Greetings. Welcome to today's session. So, if we recall, we were looking at the concept of equilibrium state and stability of an equilibrium state in the previous classes. So, let us build on that today. So, we will do an example to motivate some interesting concepts. Okay, so let's get started with the example. So what I'm going to do is essentially demonstrate or like introduce a few critical ideas by doing some specific examples. Okay, so let us consider the second order system whose dynamics is given by the following equation. Okay, so essentially when we write consider the system with equations, so it is understood that we are talking about a corresponding dynamic system whose state space representation is given by these equations. So what is the state equation? The state equation, let us say it is given by x dot equal to -1, 0, 0, -2, x of t plus let us say 1 and 0 u of t. Okay, so that is the state equation, and the measurement equation is going to be 1, 2 dotted with x of t. Okay, so that's what we are going to have. Okay, so this is essentially the state equation and the output equation. Okay, so this essentially becomes the state space realization of this particular system. So if we look at these equations, okay, so I'm just going to rewrite the state equations as two state equations. So we see that the state matrix is diagonal. So we can rewrite the two state equations as x1 dot is equal to minus x1 plus ut, and x2 dot is equal to minus 2x2t. That's it, right? So if we expand the two state equations and rewrite, so we can observe something interesting. Okay, so first thing to notice is that like the state matrix is diagonal. Okay, so we have a diagonal matrix as the state matrix in this particular example. That is point number one, and we immediately observe from writing the equations in this manner the fact that we have a diagonal state matrix. Okay, we can immediately observe that the evolution of a state variable depends only on itself and the input. Okay, so that's a very interesting observation, right? Itself and the input. Okay, so that is another interesting observation that we can make. Okay, so we can observe that x1 dot is equal to minus x1 plus u, x2 dot is equal to minus 2x2. So we can observe that the evolution of x1 depends only on itself, right? Because x1 dot depends only on x1 and u, right? Similarly, x2 dot depends only on x2, right? It doesn't depend on x1. So this is a very special sort of realization, and this is what is called as a decoupled realization. So what is a decoupled realization? It is exactly this. Okay, that is, it is a state space realization wherein the evolution of a state variable depends only on itself and the input. Okay, it does not depend on the other state variable. Or in other words, the ordinary differential equation that characterizes the state variable is a first order ODE, which does not involve any other state variable other than the ODE under consideration. Okay, so that is the bottom line. All right, so that's why it's called as a decoupled realization. All right. When we have a diagonal state matrix, we have a decoupled realization. And I hope we recall another advantage of a diagonal matrix, right? So when you have a diagonal matrix, if you want to calculate the state transition matrix e power 80, the calculation is very simple, right? So we just need to form another diagonal matrix whose diagonal entries are the exponentials of the original entry, right? So it becomes very simple. So we see that this is a decoupled realization with a diagonal state matrix. So what do we have from this realization? So let's do the usual process. So let us first calculate the equilibrium state. So as we know, we want to calculate AX star to be equal to 0. Of course, let me do this one more time. Of course, since the matrix A is invertible, automatically we know that the equilibrium state is unique and it is the origin, right? But anyway, we will do it one more time. So this is a state matrix A, and the equilibrium state X star has two components, X1 star and X2 star. If we solve this equal 0, we immediately get that X1 star is equal to 0 for the first equation, and X2 star is also equal to 0, right, for the second equation. So this implies that the equilibrium state X star is origin. Okay, so that's something which we can immediately figure out. Right? The second point to figure out is essentially calculate the eigenvalues of the state matrix. Right? Only then we can comment on the stability of the equilibrium. Okay? So in order to do that, let us calculate determinant of A minus lambda identity equal to 0. Right? So if we want to calculate this, what will happen? This will give us determinant of -1 minus lambda 0, 0 minus 2 minus lambda is equal to 0. Okay, so that's what we will have. All right. So once we have this, we cross multiply. We are going to get -1 minus lambda. Okay, here multiplying -2 minus lambda is equal to 0. So then immediately we get lambda to be -1 and minus. Okay, that's one. Okay, so we immediately observe that both the eigenvalues are negative. So the equilibrium state is asymptotically stable. Okay, so that's something which we can immediately figure out, right, from this particular example. Right? Both the eigenvalues are in the left of complex plane, so the equilibrium state origin is asymptotically stable. Okay. Next, we are going to calculate the transfer function. So let's do the next exercise wherein.
Sir, one doubt.
Yeah, please.
In the matrix, the diagonal matrix, whether the diagonal elements are eigenvalues, can we take like that?
Yes. So when you have a diagonal matrix, the diagonal elements are the eigenvalues. Correct.
Okay.
Okay. Yeah. That's a correct point. So just to reiterate, if you have a diagonal matrix, the diagonal elements will be the eigenvalues of that matrix. Okay, that's a special case. The diagonal matrix. Okay. Yeah. Okay. So going ahead, let's calculate the transfer function for this system. Okay. P of S. As we know, it is going to be C dot psi minus A inverse P plus C, right? So that is the relationship between the state space realization and the transfer function, right? So we know what C, A, B are. So let's write it down. So C is 1, 2, that is the row column vector 1 and 2. S I minus A will give us S plus 1, 0, 0, S plus 2. Okay. Of course, we need to take the inverse, and vector B is 1, 0, and the element D, the direct corresponding to the direct transmission term is anyway 0, right? So we don't have. So now, if we want to figure out the inverse of this matrix, what we need to do? So we need to take the determinant, which will be 1 by, we need to take the reciprocal of the determinant. Determinant is s plus 1 times s plus 2, so we get 1 by s plus 1 times 2. And then we take the adjoint matrix. In this particular case, we just swap the diagonal elements and we get the adjoint matrix, right? So that's the goal, all right? So now if we divide this, we immediately see that if we take the determinant within the matrix and divide the terms, so we will have 1 by s plus 1, 0, 0 and 1 by s. So as the inverse of this matrix. So we can immediately observe that this is also a special case, okay, with a diagonal matrix. So when we have a diagonal matrix, the inverse of the diagonal matrix is once again a diagonal matrix with the diagonal elements being the reciprocal of the original elements. Okay, so that's how it will work. All right. So let me reiterate this property also of a diagonal matrix. That is, when we want to take the inverse of a diagonal matrix, the inverse of a diagonal matrix is also a diagonal matrix whose elements are nothing but the reciprocal of the original element, okay, of the matrix that we are inverting, right? So this is once again a special property of a diagonal matrix. So we proceed ahead. So this implies that the Planck transfer function in this particular case becomes the vector 1, 2, okay? We take the dot product with the 2 by 2 matrix 1 by s plus 1, 0, 0, 1 by s plus 2, okay, and then we have 1 and 0, okay. If we evaluate this, what are we going to get? First, we need to multiply the inverse of matrix with the column vector 1, 0. So if we do that multiplication first, we are going to get 1 and 2. We take the dot product with if you do the dot product, we are only going to get 1 by s plus 1 and 0. Okay, so that's what we are going to have. Now, if we take the dot product of 1 and 2 with 1 by s plus 1 and 0, we get 1 by s. Right? So, in fact, we observe that the Planck transfer function by this evaluation comes out to be 1 by s plus 1. Okay. So this is the Planck transfer function that we are getting, and the pole of the transfer function is at -1. Okay. So now this is something which is very interesting, right? So I hope the process of calculating the Planck transfer function is clear, right? So we just use the state space realization to calculate the Planck transfer function. Okay. But when we use the formula to calculate the Planck transfer function, we observe that we get a first order transfer function, right? But as we know, we started off with a second order system, right? So the question that immediately comes to our mind is the following: how do we get a first order transfer function? Because you can immediately see that the transfer function is of order 1, right? So the denominator polynomial is only of order 1, right? So the question that immediately comes to our mind is the following, right? How do we get a first order transfer function when we started off with a second order system? Okay, so that is a interesting question, right? Is it not? So the answer to that question is that there was something called as the pole zero cancellation. Okay, so in this particular transfer function, if we started with the governing ODE of the system, okay, and take the Laplace transform, what will happen is there will be a 0 at -2, which would have cancelled with the pole at -2. Okay, so that's what would have happen. Okay, so essentially we have this particular whole zero cancellation happen, and due to that reason, this system, you know, appears to have a transfer function that is of order 1, right? So essentially, this looks very, very interesting, right? So because we have something called as a pole zero cancellation happening, and this essentially leads to the transfer function being of a lower order than the order of the state space. Okay, such realizations are what are called as the non-minimal realizations. Okay, so initially I told you that when we started with the discussion on state space representation, that the poles of the transfer function and the eigenvalues of the state matrix are the same, provided we have what are called as minimal realizations. But when we have pole zero cancellation, we get into what are called non-minimal realization, wherein you see that the set of poles, okay, is smaller than the set of eigenvalues, right? There are two eigenvalues, but there is only one pole. Okay, so you can immediately see that when you have pole zero cancellations and what are called non-minimal realization, the set of eigenvalues is a subset. Okay, is a smaller subset when we compare. Sorry, set of poles is a smaller subset when we compare it with the set of eigenvalues. Alright, so that's something we need to keep in mind. So now, how does this impact us? Okay, see, that is the important question, right? Is it not? Okay, all this mathematics is fine, all right? How does it impact our control design, right? Which is the focus of our course. Okay, so to answer the question, let's proceed. Okay, so once again, to recap, what I am doing is that like I am taking a very specific example and motivating some general concepts, right? So that's what we are doing. So going ahead, we can immediately see that the state equation and the output equation can be written as the following in this particular case, right? So once again, we are doing the decoupled realization. So x1 dot is going to be equal to minus x1t plus qt x2 dot t is going to be equal to minus 2x2t. Those are the two state equations. And the output y of t is going to be equal to x1t plus 2x2t. Okay, so these are the three equations. All right, the two state equations and one output equation. Okay, so now what we are going to do is that we are essentially going to have a graphical representation of these equations. Okay, so before we go into a graphical representation, we can immediately see that from the first equation, the state x1t is influenced by the input u of t, right? So we can straight away see that, right? We can straight away observe that x1 dot t minus x1 plus u, right? So the input u influences the state x1, and the state x1 also contributes to the output y of t, correct? So because y of t is x1 plus 2x2, so x1 appears in y, so the state x1 also contributes to the output y. Now, if you look at the state x2, the state x2, its evolution depends only on itself, right? So it doesn't depend on you. So, but however, the state x2 contributes to y, okay, the output y, because if you can immediately see that the output y of t is x1t plus 2x2. Okay, so that is something we can observe. So this essentially brings in some interesting results, okay, and phenomena. So once again, to summarize, we can observe that the state x1 is influenced by the input u and also contributes to the output y, right? And the state x2 contributes to the output y, but it's not influenced by the input, right? Why are we doing this? Why are we going to do this? Because if you go back to the place where we started from, right, our visualization of a dynamic system being an entity to which we provide an input u and we get an output y, we are going to redraw this entire system dynamics to that fact. Okay, so please follow along with me how I am going to draw a graph, get a graphical visualization of this particular what is a system. Okay, so first let's start with an integrator. Okay, I will start with an integrator, and let's say the input to the integrator is x1 dot. Okay, so obviously when we give a signal to an integrator, we get the integral of the signal, right? So the integral of the signal is going to be x1. Okay, so that's what we are doing. Now, what is x1 dot? X1 dot is minus x1 plus u, right? So let's say I take x1, the signal, right, and multiply it by minus 1 and give it back to the summing function, and I have the input u coming in, okay, and I multiply the input u by 1 and I give it here. I add these two. You can immediately see that x1 dot is equal to minus x1 plus u, right? So we can observe that we have got the first equation, right? Yeah. Okay, so we immediately have a graphical visualization of the first state equation, and I'm sure all of us are with me there, right? So once again, if what we are saying is that like we are going to draw a graphical visualization of this equation, wherein we have an integrator. The input to the integrator is x1. Obviously the signal which comes out of the integrator will be x1, and then we take x1 multiply by minus 1, we take u multiply by plus 1, and we add them. That will be x1 dot, right? Because why? X1 dot is minus x1 plus u, right? So similarly, we draw the graphical visualization for the second state variable. So if we draw an integrator, so let's say we have x2 dot t. The integral will be x2. Now what we have is that like we have x2 dot to be equal to minus 2x2, right? So we take minus 2, we multiply. Of course, there is no u term, so we just give it back, right? Because x2 dot is going to be minus 2x2, right? So that's what we are having, right? So we have sort of like drawn the what is it? The two graphical visualization of the two state equations. Now we go to the output equation. Output equation, if you look at the output equation, the third equation here, so we immediately see that y of t is x1 plus 2x2. So what we do, we take x1, we multiply by 1, we take x2, we multiply by 2, and then what we do is that like we add them. Okay? So I take it to summing function, I add them, then we get y. Right? Is it not? So I hope it is clear. Okay. Now, this entire block is our system. See, if we visualize a system as an entity to which we provide an input and we get an output from it, we can immediately observe that this entire block which I am drawing surrounding the integral blocks and the other signal blocks is our dynamic system, right? Because we have our input u going into the system and output y coming out of it. Okay, so this is our dynamic system. Okay, so what we have done is that like we have obtained a graphical visualization for the representation that we started off, or realization that we started off. Okay, so once again, the important point, I'm reiterating the important point, we can immediately observe that the state x1 is influenced or can be regulated by the input. However, the state x2 cannot be directly influenced by the input. Okay. Now, if you look at the output, both x1 and x2 contribute to the output. Okay. So in fact, as I told you at the beginning of this class, I am going to use a specific example to make some generalization. Okay? So one needs to be very careful when we do such activity. So now the question that arises is that, like, what is the general result that I'm going to write down? Of course, please note that this is an example where we had a decoupled realization, right? So and then we had our state matrix to be a diagonal matrix. Okay. So from this example, what we are going to write down are two general conclusions. Okay. So the state x1, we can observe that the state x1t can be regulated to any desired value by providing a suitable control input. Okay, because we can immediately observe that if you go back, or even if you go to this visualization, we see that we can regulate the value of x1 by adjusting u, right? Is it not? So such state which can be regulated using the control input, or what are called as controllable state. All right. So that is the notion of when we call a state to be controllable. So when do we call a state to be controllable? A state is said to be controllable if its value can be regulated by adjusting the value of the input u of t. Okay. On the other hand, we note that the state x2 is not controllable. Okay, by this notion. Why? Because we cannot regulate the value of the state x2 to any desired value by adjusting the input, right? So it is what it is. So we cannot adjust the value of the second state variable x2. All right. So that is why the second state x2 is said to be uncontrollable. Okay, not controllable. So some people will call it uncontrollable. All right. So of course we should once again I'm repeating it again and again. So essentially, we immediately observe that we have a decoupled realization where we have a what to say diagonal state matrix, and consequently we have the what to say the state x1 being influenced by the input u. However, the state x2, right, it is not, right. So that clearly shows us that like the state x1 is controllable. However, the state x2 is not. All right. So that is something which we can immediately infer, okay, from this exercise. Of course, see, it is not necessary that you should explicitly come in a state equation all the time. Okay, it is just that like we use the diagonal representation to understand this physical phenomena. If the state matrix is non-diagonal, then it is not necessary that you should explicitly appear in all the state equations. We will discuss this as we go along. Okay, so we will do some examples in the upcoming classes, which will clarify this statement. Okay, so this brings us to an important concept in state space as to what is called controllability. So why this notion of controllability becomes important? This notion of controllability helps us in designing controllers, okay, using the state space. So we will be using this notion as we go on. But what is this notion? So once again, I'm only going to write the definition and also state the criteria. Okay. So let me explain what this notion of control is. So let us say we have a second order system, okay, and this is the origin. The question that we are asking, when we ask whether a system is controllable, is that if we start from a non-zero state x naught, okay, can we design a input which will take us to the equilibrium state? So this is the equilibrium state. The origin is the equilibrium. So the question is, like, can we design a controller which will then calculate an input u of t and take the non-zero initial state from that to the origin in a finite interval of time. Okay, then only we are asking, of course, whether the system is controllable or not. So let me give you an example, for the automotive domain. So, for example, let us say we want to control a car, like along a specific path. Okay, so nowadays everyone talks about autonomous vehicles, right? So, let's say we are given a predefined path. We want to ensure that the vehicle goes on that path, right? So then what do we do? Like we need to essentially adjust the steering input such that the vehicle goes on that path. However, it is not necessary that the vehicle remains is exactly on the path to begin with, right? So the vehicle may be slightly offset from the path, and also its orientation may not be along the path, right? So if we take the error in the lateral displacement and also the error in the vehicle orientation as state variables, initially those errors will be zero. Correct. Sorry. The errors will be non-zero, right? Because obviously the vehicle is not going to be exactly on the path, all right? So we have an initial state which is non-zero. Now the question that we are asking is that can I calculate a steering angle input through some well-designed controller such that I can make these errors go to zero in a finite interval of time? So what do I mean by that? By that, I want to ensure that I am able to make the car go on the specified path within a very finite interval of time. Okay, so that is what we mean by controllability. Okay, so I hope the notion of controllability is clear, right? And where we apply it in practice. So let me write down the definition, and then like we will also write down the condition. Okay, so let us consider the LTI system governed by x dot e is equal to axt plus dut. We are considering a remote system in general. Okay, so y of t is cxt plus du. Okay, so this is our state space realization. Okay? Now, what we also assume is that the origin, sorry, that the origin be the equilibrium. Okay, so if the origin be, let the origin be the equilibrium. Now, the question is the following. Okay, given any arbitrary initial state x0, okay, can one find an input u of t such that would drive the system state, drive the state to the equilibrium state So, in fact, like many people will use the term to the origin, right? That's because we are assuming that the equilibrium state is the origin, right? So, to the origin in finite time. Okay. So, the key phrase here is finite time. Okay, this is the key phrase. All right, because see, if we have a stable system, what we will later infer, right, is that like anyway the errors will go to zero as t tends to infinity. Okay, so if you have a stable system, like what will happen is that like the states will anyway, if you write the states as errors and let's say position and orientation, right, as in the autonomous vehicle example, anyway the states will go to zero or the equilibrium state. As t tends to infinity, but in practice, we cannot wait for infinite time, right? Isn't it? So that is why we are looking at what to say motions associated with finite time. So there is a definition, okay, which is motivated by this question. So in fact, a system is said to be completely controllable if given any arbitrary state. So we are essentially writing the corresponding response, right? Given any arbitrary initial state extra, and input u, the interval 0 to t, where capital T is a finite number, right, can be found that will drive the state to the origin. Origin is the equilibrium state. Okay. So, bracket, let me write the equilibrium state, sorry. To the origin, equilibrium state in finite number. Okay, so that is the notion of complete controllability. Okay, so this is the definition. All right. So once again, like you see, the definition is fine, but how do we solve problems? So essentially, write down the equivalent criteria. All right. So a necessary and sufficient condition. So once again, I'm writing down only the final result. Like I'm not proving all these results. So necessary and sufficient condition for a class of LTI systems, right? LTI causal system to be completely controllable is that the rank of the controllability matrix controllability matrix. Okay, so let's say we call that some script C. Okay, shall be equal to n. So where n is the order of the system, okay, shall be equal to n. Okay, so where n, as we know, is the order of the system. So what is this controllability matrix? Okay, so for a MIMO system, multiple input, multiple output system, this controllability matrix is written in this way. So we have the matrix B, and then what we do is that like we calculate A times B, we stack it up. Then we calculate A squared B, and then we stack up after AB. Like that, we keep on going till we calculate A power n minus 1 times B. Okay, so that is how we calculate the controllability matrix for a memo system. Okay. So in fact, if you look at the size of the matrix, if you recall, the size of the input matrix, right, is essentially we took it as n by m. All right. So A times B will be another n by m matrix, right? And A square B will be another n by m matrix. Like this, there are n by n matrices. Okay, so the size of the controlability matrix will be, it will be have n rows and nm columns. Okay, so that's how the dimension of the controlability matrix will come up in a memo system. Okay, so I hope this is clear, because for a memo system, the input matrix in general we take it as a matrix of dimension n by m. So then AB will be a n by n matrix, A squared B will be a n by n matrix. Ultimately, till A power n minus 1 B also will be a n by n matrix. So what we are having is that we are having n such n by n matrix stacked besides one another, right? So totally there will be n rows and n times m columns, right? So that's how we get the controlability matrix for um, okay. So let's put as subscript C. Okay. Sometimes like we use this subscript C to sort of like illustrate that it's n by n. Okay. So then if we look at a SISO system, what happens in a SISO system? Okay, in a SISO system, we know that we have only an input vector, right? So we have the input vector B, we have A times B, we have A squared B, all the way till A power n minus 1. Okay, so that's what we have for a single input, single output system. Okay, because now B is a vector, right? So we know that B is a vector of order n. A times B also will be a vector of order n. A squared B will be a vector of order n. Like that, A power n minus b 1 b n minus 1 times b will also be a vector of order n, right? So consequently, for a single input, single output system, this controlability matrix will be a square matrix of order n by n. All right. So this is how the controlability matrix is defined for memo and SISO. Now the criteria for complete controllability is that it doesn't matter whether we have a memo system or a SISO system. The rank of this controlability matrix should be n. Okay, so that is the criteria, all right, for controlability. That is an important result. Okay, so what we will do is that, like, I will stop here for today. Tomorrow, in the next class, what we are going to do is that, like, we will come back and then, like, do many examples through which we understand this notion of controllability, and also we will learn what is called as a controller canonical form. Okay, so if you recall, initially I told you that we will learn some what are called canonical forms, which will help us in writing the state space representation of any dynamic system. So we will learn one such form in the next class. Okay? So I will stop our discussion for today here, and then we will continue in the next class. Are there any questions? Okay, so there are.
So this rank of the
Please
this
go ahead.
rank of this rank of the matrix, what it is the same as the rank of the matrix, which is, for example, 23 rank.
So the rank of a matrix is equal to the number of linearly independent columns or linearly independent rows. Okay, that we learn in basic mathematics, right? Matrix algebra, right?
Yeah.
It is the same notion, rank of a matrix.
Okay.
Okay, so you are correct. So we will tomorrow in the next class, when we do examples, we will revisit this definition. We'll also figure out how to calculate the rank of a matrix.
Okay. Thank you.
Okay. Okay. So if there are no further questions, I will conclude today's session. Thank you.